Welcome everybody. It's time to start the talk today. It is a great pleasure to introduce Dr. Prasad. He is currently a SUNY Distinguished Professor of Chemistry, Physics, Electrical Engineering, and Medicine, and also Samuel P. Caton Chair of Chemistry, and also Executive Director of the Institute for Lasers, Photonics, and Biophotonics. So far, he published more than 790 scientific papers, which is a lot. I mean, not just a lot, huge number of papers in the four different fields, such as nonlinear optics, biophotonics, and nanophotonics, and nanomedicine. And also, he edited 8 books, and also he has also numerous patents. And also, he is a fellow of APS, OSA, and SPI, and IEEE. And also, in 2005, he was selected as the top 50 science and technology leaders in the world by Scientific American. And because of his the achievement and contribution to various scientific communities, he received many prestigious awards and medals, such as Bowley Medal, and Guggenheim Fellowship, a Sloan Fellowship, and also Western New York Healthcare Industries Technology Discovery Award, and SUNY Excellence in the Pursuit of Knowledge Award. And there are so many actually. I cannot say anything but more. I cannot say everything here, but one of them is a SPI Highest Honor of President Gold Medal, and Optical Society of America's Michael Field Biophotonics Award, and also recently he got IEEE's Pioneer Award in nanotechnology, and was Peter DeVry Award from American Chemical Society. So every society actually they awarded him because of his great achievement. And also Dr. Prasad has received the honorary doctorate from KTH Sweden, and also ex-Marseille University in France, and also MEPHL in Russia, and Federal University of I don't know whether I'm speaking correctly, in Brazil. So it's a great honor to introduce you, Dr. Prasad. Let's welcome the speaker today.
I just want to see whether this is the PowerPoint. No, I want to see whether it's on.
Yeah, it's on. Yeah, it's on. I think it's on here.
It's on? Is it on?
It's not a microphone, it's only with audio.
Oh, okay, got you. Okay, this is a microphone here.
Here, this is the pointer, and you can move.
Well, thank you, Sungjin, for this very generous introduction. It's always a great pleasure to be introduced by our former star student, Professor Sungjin Kim got his PhD from University at Buffalo, and actually I served as a co-advisor to him. So I'm very delighted to be here. And first of all, I would like to thank Dean of Engineering, Professor Bardet, for this invitation from the engineering. And I also like to thank Professor Abdel Muttalib for hosting me today and spending most part of his day today with me. And so it is late, and it is almost a dinner time for most of us. And I had a long day, but my spirits are really, really revived, seeing all these young minds sitting here, very impressionable. And so I'm going to talk to you about an area that I consider, very important societal area, and that's nanobioengineering and nanomedicine, and because it promises to provide revolutionary input to healthcare, addressing many healthcare challenges. This is also an area which is multidisciplinary, and this is the new way of doing science, and technology. That is bringing together different disciplines. So we created an institute, as Sungjin said, some 20 years ago. It's called Institute for Lasers, Photonics, and Biophotonics. And those of you, if you can read, it is here. This institute, this is our website. This is really a multidisciplinary center integrating different disciplines. And so what we try to call is convergence of disciplines. This is a very important aspect of modern science and technology, bringing together different disciplines to create and measure impact. So in our area, we've been bringing together engineering, chemistry, physics, biomedical technology, physics is over here, photonics, and nanotechnology, interfacing all of them together, nuclear technology. I can't read from here. And if I stand here, the microphone is here. So
it's okay. Give it smaller.
yeah. So one theme to create a high societal impact, whether it's energy, whether it's healthcare, whether it's environment, you need to bring together convergence of disciplines. And that's what we do. The second one is that many of these challenges are global challenges. They are not just a regional or national problem of one country. So we really truly practice science without border, working together with international community. So our programs are actually interacting with many different countries in practically all continents in our institute. And so we are engaged in multidisciplinary research. We have extensive research facility, training program, working with industry. Industrial partnership is a very important program and an aspect, and I was very happy to hear from the Dean how you have made also a major thrust of your program integrating with industries. Collaboration, technology transfer is another important aspect that not only should we just be publishing, but we should also try to see how we can transition it for benefit of society. So we have been very proactive in transferring, and these are 9 spin-off company examples of that. They are not just all in the US, they are also distributed. Nanobiotics being in France, and some of this company in Hong Kong. So anyway, they're across the globe. Now I wanted to then again emphasize that this area of nanobioengineering, nanomedicine, has many important components, contributions from basic sciences involving nano and chemistry in terms of design synthesis of nano building blocks, interface engineering to connect the artificially made material with biological insights, and multi-scale modeling to control a structure-property relationship. Physics, you will see an example of that. Biology, again, through understanding targeting and biorecognition principles to target, to make diagnostics and therapy more effective. Engineering is a central theme that comes in many ways through hardware and software coming together to provide you a major input in this area. So we can look at it, contributions from different aspects of engineering, electrical, computer engineering, you're looking at biomedical engineering, you're looking at material science and engineering, they all come together, software, computer, over here, data mining, artificial intelligence, you're looking at medicine aspect, diagnostic, therapy, and nanopharmacology, nanotoxicity, understanding the toxicity effects created deliberately by nanoparticle or accidentally, what they can do, that's an important part. And then combining therapy and diagnostic, there is a new term called theranostics. Okay, so nanotheranostics is an important aspect of this nanoengineering and nano. So all together, again, integrated program, multidisciplinary program, forming the bridge between these different disciplines. So I want to give you one example now. And that example is of nanophotonics. This is connecting nanotechnology with photonics. And photonics, to remind you again, is a light wave science and technology. Science and technology utilizing light, right? That's photonics. And combining that with the nanotechnology bridging is what we call nanophotonics. And so you can manipulate the properties of photons and its action, okay, in a healthcare regard. So one example is that you can control their optical properties in nanoscale. And a beautiful example is size-dependent optical properties in semiconductors. These size-dependent properties mean that the same semiconductor, like quantum, you can say cadmium selenide, cadmium sulfide, and if you make them in nano size, ranging from few nanometer, 1 nanometer to few nanometers, their optical absorption and emission become size dependent. This is a beautiful example of quantum effect, okay? And so that's one example. The other one is in case of metallic nanoparticles, that when you go from bulk metal to nano-sized metal, they are no more reflective, but they become transmitted with different optical properties. New kinds of transitions appear. And that I try to address in a book, monograph called Nanophotonics, which is translated also in Chinese. And these nanophotonics has a major impact in the area of solar energy, information technology, healthcare, and environmental monitoring. I'll give you some examples of that later. So here is an example of what happens in the bulk semiconductor. You have valence band and conduction band, and you have a gap. And you can take a transition from here to here to create a photodetector or photoconduction mechanism. Also, by doping, you can create states in the middle, and you can do the electronic circuits. You can also harvest photons by this mechanism to create photovoltaic effects. But when you go into nanoscale, these band pictures don't hold, and you have discrete molecular-like states. That's called quantized states. And then you can have these transitions, and the gap now is size dependent. So a smaller size will absorb in a wider region, and bigger size will absorb and emit light in more towards red. Okay, so here is showing the examples of cadmium sulfide selenide. So the small size is absorbing and emitting in the blue, and these are the materials that we have made through chemical approach, solution chemistry. So they are dispersed in a solvent, and the bigger size is emitting in the red. Okay, so these are, you can tune their band gap now by size, and you can utilize them for many different applications. And they can cover a whole spectral range from all the way from UV to visible by one single chemical composition, just size effect. Beautiful. And you will see examples of that here. So we have developed through our chemistry program, these chemical methods that we can make them these dispersants of the nanoparticle, colloidal dispersants of different sizes, and apply them in applications in solar energy, applications in sensing technology, application in diagnostic and therapy in nanomedicine. I'll give you an example of that. And they cover all the way from UV to IR. Another method we have used is with silicon, because these materials we can make with different semiconductors, and cadmium-based lead-based system has certain applications. But for healthcare, if you talk to a medical doctor, our program involves actually practicing physicians as well. And when we talk to them that we are going to use cadmium selenide, they said, no, we don't want cadmium selenide. They're toxic for biological applications. So we moved into trying to make silicon quantum dot. Silicon is also a semiconductor, okay? And it's earth-abundant material. And also because you have lots of silica. And the other thing is they're biocompatible. So we started working on making silicon quantum dots. So again, the size-dependent optical property of silicon. And here we use another chemistry, gas phase chemistry. So we take a silane gas and we pyrolyze them with laser, and then we can say laser assisted, then you have these silicon atoms, they cluster together, and they form silicon size, certain size nanoparticles, and then you cap them. So that's how you do this. And then we etch them to clean their surfaces and passivate by coating it with some organics, hydrogenated one. And so these ones are highly luminescent. Bulk silicon is not much luminescent. That's why you use them for photovoltaics, because they don't emit back light. They create carriers. Okay, but when you go to nano size, they remain confined, electron and hole, and they become highly emissive. And so we use them for many biological applications. We can encapsulate with bigger nanoparticles in envelope, put them targeting group antibodies to target certain biological site and use for bio applications. Can you hear them in the back? Can you hear me in the back? Loud and clear? Okay. All right. Okay. So here, I want to give you another example of integration of nanotechnology with photonics. And I label them what we call them optical nanotransformers. So these are nanoparticles that contain rare earth ions, and we create them again through solution chemistry dispersed in either organic solvents, if you are looking at some technological applications, in water, if we are looking at them for bio applications, they have this advantage that they can take a near IR light or IR light, longer wavelength, that can go deeper into materials because there is less scattering and very little absorption. And then when they encounter these nanoparticles, that near IR light gets absorbed sequentially and get converted into different shorter wavelength light. And that's what it's called. This process is called up conversion. You take near IR, longer wavelength, less energy, and convert them into shorter wavelength, which you may need for activation of different processes. And so that's why we call them optical nanotransformer, on site, on demand, converting photon from one wavelength to the wavelength you need over there, okay? And they occur by different mechanisms. One mechanism is climbing through ladders, sequential absorption of low energy photons, and then being emitted as higher energy, or the two ions nearby exchanging energy, one going up and the other coming down. Okay, so this is called energy transfer. So we make these kinds of materials and control their physics so that this particular channel, whether blue conversion we need is maximized or green conversion we need, and all these efficiencies in any case. The other one is reverse, and you will see examples of that. It's called quantum cutting, where you take a deep UV light or visible light and it gets absorbed to higher level, and then, excuse me, it jumped so many, and then it can sequentially emit two lower energy light as quantum cuttings. You take higher energy, cut it into others, and you see application of that too later. And these ones we can effect because they are linear process with a very low intensity light. You don't want to have high power laser because that limits its application, okay? So we use that, and what we call quantum dot technology is one example of the quantum dots that we have made, and they are from photovoltaics to quantum dot lasing to IR photo detection, bio applications, and in communication, optical communication. So we have programs doing all these. And the other one is this up conversion one, where we are looking at converting the near IR light, whether at communication wavelength or 980, these power sources, light sources are readily available, converting them to another IR or converting them to ultraviolet 350 or to visible light. So you can see clearly this application not only in biology, as I will show you later, but also simple application night vision. You have IR light converting into visible, okay, or security marking. So here the idea is again understanding the physics. Then only you can manipulate its property and which channel you want to use it. Okay, so we bring in physics over here to control the local environment, the lattice we choose, the energy transfer processes and all those. This review is a very good review that talks about how we can integrate this with nanochemistry to design efficient optical nanotransformers. Okay. Another example of showing to you is how we enhance the efficiency so that we can use a very low power CW light source, whether it is from a laser diode or even LEDs. And for some application, we want to upconvert sunlight. Can you upconvert sunlight through using the nanotransformer? So we try to produce ways in which we can enhance the efficiency. And so this is hierarchically built structure that your dean talked about molecular engineering. This is an example in a way molecular engineering where you can build hierarchical structure with these antennas. They absorb light and then the transfer, and then through there they reach the core which does upconversion. So here we have designed a structure where you have dyes, antennas that absorb light, a transfer to a shell over here which is neodymium, and then that transfer to another shell over here or core, ytterbium, and ytterbium ion transfer to thulium that does upconversion. So all these are harvesting of photon and sensitizing thulium. Okay? And this kind of nanostructure, we are talking about altogether 30 to 40 nanometers. Okay, only that size. And what it does is that enhances the upconversion 100 times. So that you can see this lamp light, incoherent light source, a very low power being upconverted all the way into blue and UV. Okay? 100 times enhancement, a world record. We put is 19% efficiency. That's our record. This came in this nano-letter paper. And you may say, oh my God, there are so many steps involved, and each step has certain probability. Process should be very inefficient. Each process has certain steps. It's reverse. This multi-step transfer is much more efficient because of the physics involved. Each step is a little trickling down in energy, a little bit here, a little bit here, a little bit here. So it trickles down very efficiently, fast, finds the pathways. Okay. Again, we have used upconversion technology for many applications. I will give you just a very quick example in area of solar energy and jump to nanomedicine. Okay. So let me just give you, I know the talk is in more of bio application, but I just wanted to show you a little bit about solar energy. And another example is because this is Sungjan's work over here also involved. Okay, when he was there as a graduate student. So one part is that, look, if you look at photovoltaics and solar panels, silicon, for example, silicon is very efficient in converting, absorbing light in the green region towards a little red over here, its band gap is over here, and then it converts it into charges. Okay? But it doesn't do anything in the IR. Okay, these are not absorbed by current silicon panel. Also in the UV, you absorb light, but it doesn't need that much energy. UV energy is this much. The band gap in silicon is only this much. So this extra energy is wasted as heat. Okay? So it doesn't efficiently, when you look at one photon taken in and convert into one electron hole pair, a lot of energy is wasted as heat. So what we showed is that we can use the quantum dots, which are longer wavelength absorbing. And they can be coupled to in this sequence absorb light and then separate the charges when it's connected to single wall nanotube, and that turns as a conduction of charges into a matrix. So we optimize each step by using quantum dots to harvest over a broad range and IR harvesting. So that addressed this issue. We published over here and we have continued to work in that area. The other one is this area over here. So one mechanism was that we can use these nanoparticles, lead selenide, and when we excite it into high energy level, it can break into 2 excitons of lower energy, and each of them can give you an electron hole pair when they separate. So you have carrier multiplication. So one photon generating more than 1 electron hole pair multiplies the carrier, so gives you higher efficiency. This is what Sungjin showed over here. Okay. The other one is using this Photon Up Converter. And the idea is that you can again take this IR and through nanotransformer you can shift it into the visible region where it can be absorbed by silicon. Okay? And then if you take the UV, this region, and you can cut it by quantum cutting, you can make 2 photons over here that can be absorbed and multiply. Okay? So you're adding value from here and here. That's what we call photon manism by in-situ conversion. And we apply that over here. We demonstrated actually those nanotransformers, our efficient one work with sunlight, upconverts this region over here. And we showed it in silicon, in the different kind of photovoltaic cells, that it adds value. By simply adding a layer over here of on your photovoltaic active medium, you add a layer at the bottom, so all the IR light that is not absorbed, it goes through and excites this upconverter that generates light over here, which can be reflected back and reabsorbed. Okay. We also showed more recently the quantum cutting that transfers energy from here to this region where silicon has higher quantum efficiency, and it adds value, shows 6% improvement. Okay, let's go back to the main topic now, which is in healthcare. So here we are looking at nanomedicine, nanobioengineering, nanomedicine. What we are utilizing is nanoprobes for early detection of diseases, looking at drug-cell interaction, and real-time monitoring therapy, these nanoprobes, okay? And how do we do it? Through imaging, as you will see. And the other one is light-activated and guided therapy, and tandem therapy, a number of therapies combined together using a single nanoparticle, okay, platform, okay? And so there are books. Biophotonics is one book, shows about power of light for that, diagnostics and therapy. And more recent book that I wrote is called Nanomedicine and Nanobioengineering. That actually gives you more direct input into how it actually, how close it is actually to treating patients. Okay? So the first is a nanoplatform. A nanoplatform, what functionalities you need for nanomedicine? One of them I showed to you, optical. So you can do optical imaging or light-activated therapy, okay? The other one is that you can use magnetic, okay? Magnetic imaging, MRI, we routinely use that. So magnetic properties, or also you can use magnetic therapy. Magnetically in AC field, you can heat the nanoparticle and you do thermal therapy, okay? And then you can do also incorporate radioactivity in nanomedicine, and you can do radiation therapy, or you can do radiation imaging, radio imaging and all those. And then you can control biological function of that provides you, like, you don't want these nanoparticles to wander around and do things all over. You want to put targeting group that recognizes the disease site and attaches over there, where you can do diagnostic and therapy. And the other one is you can also utilize in that local environment enzymatic control. So there are excess enzymes expressed, and that enzyme, you want to make you can make a nanoparticle, there's the enzymes that chop off those nanoparticles and release things. Okay, so enzymatic release. So we manipulate that. Now, what are the advantages in addition to that of using nanoparticle technology? Suppose you are using it as a payload of chemotherapeutic agent or any therapeutic agent. First one is this formulation. Many of the drugs you use are not dispersible in water. They're hydrophobic. So they cluster together and they clog up things. Okay? But when you put them in a nano carrier, you can encapsulate it so that the outer environment is hydrophilic and is dispersed. Then it can be dispersed in water and stay stable, and you can be targeting high load at the disease site, whether it's cancer or whatever. Okay. Second one is that it also prevents those drugs from enzymatic degradation. Or you're doing gene delivery, a lot of DNA that can be chopped off, but DNAs. Okay. Then you can also have targeting to enhance the local concentration where you need activity. It doesn't have collateral damage to healthy tissues. Okay, and then you can have controlled release, a sustained release. This is very important because then you don't need to take the medicine every day. You could have it time release capsules you're used to. You see those in market already. And then multimodality. The same nanoplatform can do a tandem therapy, more than one therapy combined together. And finally, you can make them so that they don't stay in the body and cause other side effect over course of time. Okay, nanotoxicity can minimize. So you want to have these nanoparticles be eliminated. And again, you can make these particles with understanding and multidisciplinary approach that integrates chemistry, physics, engineering, and biology, understanding of that. Okay, let's keep on moving. So one of them is imaging, and imaging, again, bioimaging has interface, very important concern in the interface bioengineering, software engineering, bioinformatics, hardware, where we're integrating laser imaging, and if you're looking at optical data or MR, and then here to making these probes and using microarray technology. So this is an example of using quantum dots of silicon for imaging. Okay, so we in our lab, in our institute, and again, this is the beauty of this integration, under one umbrella, one roof, we go all the way from chemistry, physics, and engineering to live animal studies. So we have imaging system. So we make these nanoparticles that I showed you, silicon quantum dot. We inject into the tail vein. This has a targeting group, as we said, encapsulation, targeting, conjugation. And then we have a mouse that we grow a certain tumor model. Okay, and then that tumor is over here. And then when we inject it, it circulates. So you need to have what is called pegylation group to enhance the circulation in blood to find time to get there. And it can localize over here in the tumor. So whole diode distribution, how it goes through around that, you can monitor optically. So we clamp it in an optical, partially anesthetized so that the mouse doesn't dance around. Okay, it's clamped in certain site. And then you can shine light in, and this is where the hardware, software of engineering comes in, your ECE, right? And it illuminates tomographically this whole mouse. And when it interacts with the silicon, we make it a larger size so that they absorb in the near IR and emit in the near IR. because that's where the light can go deep inside and come out emitted light. So silicon quantum dot, we can make it that size. And here is showing to you the image. The targeted nanoparticle in the course of time accumulate in the tumor and light up. Okay? But untargeted, you see they're wandering around, they haven't made it over here. So that's showing to you the whole distribution of going through the first site is going to be liver and spleen and all those, and then eventually they get in here. This is the targeting group. Other ones they get, okay. So the other one is this up conversion one, nanoparticle. So we make this up conversion nanoparticle, this optical nanotransformer that I was telling you about. We can excite that here around 980. And this is the plot of what we call transparency through biological medium. And it has windows. This window is called first window optical transparency from 650 or 700 nanometer to about 1 micron. So if you use light in this one, it can go deep or it can come out deep from the body. So we excite at 980 and we image light coming out up converted at 800, higher energy. But both of them are in this region. So we can show the imaging, we use it for imaging, various one, live animal imaging, as in case of silicon, or through a skull. This is human skull. And we can send light through this thick skull that's very dense, a scattering medium. But you can send light 980 through outside, and you can illuminate regions under the skull and commit emitted light coming out and image it. So that's showing the image of the spot under the skull. But more popularly, we showed that we can stack all these inches thick pork chops, and the light can go through here, this light, and excite the emission and come out. This received a lot of press attention because they can visualize it through this thing. Okay. Another imaging modality we use is photoacoustic imaging. So light is converted into, it goes in there, and our nanoparticle contrast absorbs this light and converts that into heat. And that heat now in the soft tissue creates this acoustic wave, ultrasonic wave, by thermal expansion and contraction, okay? And that ultrasonic wave now generated, I can detect it through ultrasonic transducer, in ultrasonic imaging. So it's a hybrid between optical imaging and ultrasonic imaging, okay? And that has many advantages. Again, if you use IR light to get to the target, nanoparticle absorbing IR light that I showed to you many of our nanoparticles do, and we demonstrated lymph node matching and all kinds of imaging modalities. Now, more impressively, in 2015, we showed that one nanoparticle formulation in core shell structures can provide you with 6 modal imaging. There are 6 different kind of imaging modalities: PET imaging, SPECT imaging, Cherenkov imaging, CT imaging, fluorescence imaging, magnetic resonance imaging. All these can be combined in one nanoplatform to provide a different length scale and physiological response imaging. We call functional imaging. Okay? And one simple example will be our up conversion nanoparticle as a nanotransformer. But if it is put gadolinium in there, gadolinium is a paramagnetic ion and provides contrast for MRI. Okay? So you can combine MR and optical very easily. And the same gadolinium can also serve as a CT contrast, is high atomic number element. Okay. Optical sensing, we do different kind of optical sensing using nanoparticles, using nanostructure like photonic crystals, plasmonic sensors that changes metallic nanoparticles. I don't have time, I need to move quickly. I generally pack a lot of stuff. So one of the things we work on, where we have engineering coming in there, is this surface plasma and resonance sensor that uses gold film and reflectivity from that. That reflectivity changes when its binding occurs over here from the interface. So we introduce phase shift. Generally, they do it only when amplitude shift of the reflectivity. But we also combined it with phase sensitive detection, that there is not just change in the signal of reflectivity, but also change in the phase of that signal. And so we introduced this phase sensitive sensor, and we also showed that if you use this not in direct binding, but through nanoparticle capture and attachment to it, signal is further enhanced. So here the idea was to combine selectivity with sensitivity, enhancing it so that you can, okay. Another example I want to give you is which is beautiful example again of engineering, and that is this flow cytometry, which is a simple case over here is that you create a cellular suspension. So you take the tissue in disease profiling, and you can create cellular thing, and each cell is tagged with certain antibody to detect, to be detected. Okay, so each cell is tagged through antibody and biomarker. It picks up a label, so that each cell is labeled depending on its characteristics. So disease cell is labeled separately than the other, and then you flow it through there, a single cell suspension, and optically interrogate by looking at emission and reflectance, scattering, and then this way you can do cell profiling. You can do the distribution of cell. And so here you're looking at, and these ones are flowing at a rate of 10,000 cells per second. Okay? So this is a beautiful example of how you're looking at system here, microfluidics to control the flow, illumination system over here, detection. You can miniaturize this detection, and you're looking at software to analyze this massive stream of data coming out. Okay, so we created a company called Flow Cytometer here that utilizes fiber-based system to minimize the detectors and all these components, so we can make this instrument transportable to the field, in-field detection. Okay, let's move on. This shows how nanoparticle tagging we utilize to make it more sensitive. Therapeutics, we have combined again different nanoplatform along with imaging and sensing to therapy, and applied it to many diseases: tuberculosis, HIV, cancer, addiction, and infectious disease of influenza, and skin diseases. And we work with many medical doctors who are actually practicing physicians in these. This is creating a nanoparticle which is multimodal, and it creates MR contrast as well as radiation therapy, X-ray therapy, provides that in there, and it also generates oxygen to treat hypoxia. So three things: treating hypoxia, doing radiation therapy, and providing MR contrast. Another thing we are putting is now expanding nuclear nanomedicine. So how we can incorporate nuclear probe, radioactive probes for imaging or for therapy. And one of the areas we are working on very heavily is neutron capture therapy. So here we are making boron nanoparticles that capture neutrons, and then they disintegrate, forming these alpha particles, and this lithium, the alpha particle kills the cancer, okay? Cells over here. So, so we have made these boron nanoparticles. We're working on that. Okay, another area of recent interest is in brain research. Okay, so we call it neurophotonics. So we combine light wave technology with to map out brain activities and treat brain diseases, and one of them is this cognitive deficiency. So now dementia is a big problem with the elderly population. That's the brain function not fully functioning, cognitive disorder. In children, you have rise of autism and retardation. That's lack of, again, cognitive function. Then you have traumatic brain injury, TBI. That can be through sports, youth sports. People getting knocked down, concussion, and developing brain So the idea is, can we actually, and military in case, which is non-contact brain injury from blast and others, shock waves. So can we assess the cognitive state and treat it? Okay? The other aspect of this brain disorder is created by people's habit. And opiate addiction is on rise. That creates addiction and impairment in your brain function. So we are working through this area. So the first part is functional or structural mapping of brain function. Okay, and we do it through different imaging. We are combining optical imaging, photoacoustic imaging, MR magnetic imaging. All these three we are combining and putting in a nanoparticle. But these nanoparticles, if you do systemic injection through the brain, through the blood, that has to go around and cross the blood to brain side. And that's prevented by blood-brain barrier. So we make these nanoparticles with a stealth action that they can sneak through the blood-brain barrier and get into the brain, and with targeting the localize in the site which are impaired part of the brain. And then once we can map out the brain function by imaging, is there any structural damage? Is there any change in brain physiology? That's functional image, right? Third thing we do is we also look at brain waves. The brain waves have magnetic field associated with. So engineering challenge is, can you map out that magnetic field which is very, very low due to brain wave? So we are working magneto-optic materials that will allow you, read you specifically, map out the brain wave. Okay? So these are the tools we are developing. This example is one example of treating brain cancer using targeted nanoparticle. The other part is that, wait a minute, something we skipped. Nanoparticle, biodegradable, that degrade eventually after it has done job in the brain. And it actually uses curcumin, a natural medicine, and shows that natural medicine is very effective in treating cancer. So we make the nanoparticle, we have blood-brain barrier model to test whether these nanoparticles will cross through blood-brain to go into the brain side, from blood to brain side, and then we can utilize it in vivo studies, and we showed that they are very effective in treating the brain tumor. Okay, the other one is the use of photon converter for brain research. So one of the tools to impair the brain, to repair the brain function, is what is called optogenetics. And this is a rising area. We use light to stimulate a genetic material embedded, that you embed in the brain to stimulate a neuron function. Okay, that's called optogenetics. The problem is that the light that you need to stimulate this genetic material generally is light in the visible, blue light. You can't send the blue light from here to activate optogenetic material. So what do? You use our optical nanotransformer. You send a light that goes through a skull. I showed to you the 980 nanometer light goes deep through the skull, right? And then once it gets inside, then you can actually convert that at the nanoparticle side to blue light, and that blue light activates the genetic material sitting next to it to do optogenetics. So in view of shortage of time, I just wanted to show to you that indeed we have achieved that, okay? That is stimulation, and we have shown the modulation of brain function, okay, in terms of ion activity. It's a published result. So you can look at my name and optogenetics. The paper will come. So our dream is someday, can we access the brain activity assessment and modulate and enhance it, okay, to repair the cognitive disorder or cognitive this. And so one part is imaging assessment, and the other part is optogenetics, one example. The other one is gene therapy we do. Third one is chemotherapy, releasing the drugs that enhances the cognitive state. So someday somebody might be too futuristic and say maybe we can create superhuman by these techniques to enhance the cognitive state way beyond what we have right now. Okay, so one thing you need to be another one is that we have done work on similar drug addiction, where there is a biomarkers in the brain that creates its addiction, and we send these nanoparticles to actually silence this biomarker overexpression, and that's called siRNA silencing. So we do that effect over there to do it. Okay. Another thing we do is that we want to make sure that these nanoparticles are safe. So we want to do their toxicity studies in detail. And this was the first study we reported in Nature Nanotechnology, that is in primate, which are cousins of ours. So if it's safe for primate, we would assume that it's safe for us. So we are doing studies on nanotoxicity of these. Okay. Some of the books, again, I want to refer to you. So I see a lot of opportunities, both in imaging, sensing, software, a lot of roles for engineering and nanotechnology in this area. But this integration of different disciplines is the key. And you cannot just work in isolation and say, I will do my part and hopefully somebody else will do the other part, okay? And then I wanted to also produce this theme that we really need to firstly start is thinking outside of the box. So if you are trained at something, you need to think outside of the box, connect with other discipline, and see how you can form that bridge. Then only you can create high societal impact. So once you have that idea and so on, produce an innovation, don't stop there. Try to reach out and see whether you can form industrial partnership and promote this technology transfer through either licensing or through even being an entrepreneur yourself, okay? And then have a global vision. So this is where, and I want to give one example over here of this that we did. We call it transforming fiction to reality. And this is our real success story. So this was in 1966. Many of you did not exist, were not born, right? And there was a movie and there was a fiction called Fantastic Voice. This was about a diplomat who had a blood clot, and the doctors had to come up with invention the scientists, to put medical personnel in a submarine and shrink it to nano size and inject in the bloodstream of that diplomat. The submarine is navigated to the blood clot site, and there they release the blood clot. And they had to get out of the body within 24 hours, because then it goes back to this original size. Okay, so I was inspired by that, and we made this nano clinic. So this is small silica bubble, which replaces the submarine. The targeting group on that replaces the engine to drive it, and instead of doctors and medical this, we had remotely controlled sensing and drug activation in there. And then we patented it in 2003. And we licensed it to the French company, our dean's original country, France. And this one now developed this nano X-ray that has had many successful clinical trial and is very close to patient care for treating cancer, okay? And is publicly trading now. So you can buy stocks in there. It's a $300 million company, euro company. So real success story of that. And what are the benefits to us? Our university did a very smart thing. This, you like this story, I'm almost done. Is that this company was a small company starting, and they couldn't pay the licensing fee full. So our university says, okay, pay us a little bit, and the rest of them we will take it as equity in your company. So they took this equity, and now our university then is publicly trading, cashed in all its stocks, and has millions coming out from that stock sale. Okay? So that's the kind of vision and things that you need to. So it's a real story impacted in there. So lessons learned. First of all, I want all of you young mind to think big. Think of the impossible in some ways. Take a risk. Imagine the possibility beyond perceived boundaries. I'm not saying all of them will come through. Most of them may fail. But even a few of them succeeds. You have done great, right? Something not incremental. Second one is create a link among other disciplines to achieve high societal impact. Okay, that's resonated. And so this is what we call convergence of discipline. And the third one is one planet, one world. We live in one planet, one world. So we need to really engage in science without border. Acknowledgement, and I want to particularly acknowledge Professor Sanjin Kim. I still consider him part of UB, but he's also in Miami, and we are already exploring collaboration together with new projects. And the other faculty is Professor Mark Connect, who is here from chemistry. We had shared a joint grant earlier, and we sat together before coming here to define a multidisciplinary project together in there. So, and I work with, as I said, a number of MDs, which are acknowledged here, few of them. And thank you. I don't always wear, Sanjing asked me, how come you're wearing this? You should have a tie and jacket and suit. I do wear sometimes, so I at least brought a picture of tuxedo, me dressed in tuxedo to thank you. Thank you.
So I think we have time for questions, I suppose. Do you have questions for our speaker?
Any question from the student? No? Oh, here.
You were talking about imaging of brainwaves.
Yes.
Have you made any progress on that? Or?
Yes. We have made progress in making materials. So one part is making materials that are sensitive enough to change their optical properties. That's one way. Okay. So there are a number of things we have developed. One of them is imaging tools. So we are now develop contrasts that provide very big enhancement of MR imaging. And I was just at the University of Southern California. They have a big center, institute for neuroimaging. So we are working together, they do MR. Second one we have done is we have developed photoacoustic imaging and optical imaging near IR using light to measure, again, an image. And the third aspect is this materials, magneto-optic materials that we have developed that's showing way, are you familiar with magneto-optic? So, you know, the gaze is over there, is Faraday constant. So we have made the materials with very large Faraday constant. And then the engineering challenge is, these are made with plastic thing. So you can imagine making conformable helmet, okay, to wearing it. But remember, these brain waves are very, very low level, so you have a lot of noise to filter, okay? So that one is there. Then you look at image processing. It plays a very important role in there. So engineering challenge, and how do you get light through different regions? So we have a lot of fiber optics, delivery of light through this to go in there and get change, phase change, magneto-optic. So that engineering challenge we are working with. It's a-
I'd like to ask a question if I may.
yes, you promised you're going to ask me a question. so
Well,
go
but
ahead.
I'm not going to ask you the question I promised to ask.
Yeah, okay. Ask me whatever you want.
If you look at radiation therapy, I mean, we have the traditional now X-ray therapy, and then we have the proton therapy.
Yeah.
But one of the major challenge of therapy is actually collaterals. As we send rays of some strong intensity, we damage things on the path of the rays. We're trying to focus the rays at a given point to increase locally the intensity, but yet we still do damage. We do damage, especially in the brain, and we're trying to hit particular areas of the brains. If we don't do it right, we can create more damage than good. So you were explaining this new injections of biomarkers, call them, or nanoparticles, which will target particular areas and stay there. And obviously you mentioned also that you can excite these particular nanoparticles with waves of different nature. I mean, we can look at X-rays, or we can look at possibly maybe ultrasound, which will excite through some kind of shift in wavelengths, right? And it seemed to me that if that was to be developed, we can avoid all the collateral effects of our typical radiations and use smaller intensity, much smaller intensity, and maybe we don't even have to focus the ray, because since you have low intensity, you will have enough intensity to excite locally the nanoparticles to release free radicals and destroy the cells. So I don't know, this seems to me so big. I mean, I don't know if you understand, but that can actually eradicate cancer.
Yeah. I think that you...
A very smart way to deal. Radiation therapy now costs a lot of money. A photon device, I mean, this photon therapy costs, I don't know, they are huge. They dim the light in Miami if you turn them on. They consume so much energy. Here we can do it at a much lower energy level and much safer, more practical, and less costly, if we could, you know. So I'm very excited about that. I don't know if my colleagues in the Sylvester Cancer Center are listening, but I'm sure they would be excited to know that there are new technologies on the way. But I'm sure you can expand more on that and tell us what is out there, what is possible.
Yeah, I just want, I fully, I think, appreciate what you said, because that's really the beauty of nanotherapy, is that firstly, you can enhance the local concentration by targeting. So these nano agents are in large concentration sitting near the disease site with other brain function. Second thing is that they are enhancing the efficiency of given therapy. For example, as I said, using the sensitizers, radiation, the nanoparticle, they absorb X-rays, and then they can emit this in radiation therapy. So what with this aid, you are lowering the threshold of X-ray even less and less at which you can do this therapy. And you get to the lower level where the healthy tissues, where these nanoparticles are not there, are not affected. Okay, and we already demonstrated in principle with this guy, a head and neck cancer surgeon at the University of Southern California. You were there for a while, right? So, and their Keck School of Medicine, that using our nano formulations, they lower the X-ray doses well below what they were using for treat head and neck cancer. And this surgeon is so excited about it, that this is really terrific, that you can do this precise and localized therapy as much lower doses that minimize the risk of collateral damage.
Thank you. So thank you very much. This is really giving us a lot of hope. Any more questions? All right. Well, I hope that some of you actually will follow the footsteps of Sanjin came. And, maybe Sanjin will be continuing and discussing this very important development. So, I would like to give you a little token of appreciation.
Thank you. Wow.
It's unfortunately not discrete because it's so big that we couldn't put it in a bag.
Thank you.
It's a little, you know what that is? Miami, a beach bag. But I understand there are a lot of goodies in there, so we have to keep it vertical. It's a gift from the Department of Electrical and Computer Engineering.
Thank you very much.
Again,
Oh my God.
thank you very much for your talk, and we hope to
Appreciate
see
very
you soon.
much.
Thank you.
Is there any photographer over here? No? Thank you. Good. Great. I just wanted to say that I know as a student generally are shy and they are kind of a little bit afraid to ask question, although no question is a stupid question, okay? But if you were hesitant to ask a question, you can always send me an email and asking that question, or if you have a thought, you can send me an email. I promise to answer that question, not the same day necessarily, because I'm a busy man, but I will definitely answer, will not ignore your email. And I have gotten these kind of emails from students, and I appreciated that, because that's one of the rewards I can see, that I stimulated some thought in your mind. You are our future generation. You are our future.
Thank you very
Thank you.
much. Thank you.